So hey guys, and welcome back to our data structures and algorithms tutorial series. And today we are going to be looking into the detailed comparison between binary search and linear search. So in order for us to fully understand these differences between these two concepts, we need to develop some algorithmic thinking. So we are going to play a simple game and see the results that we get from linear search and binary search in terms of performance. So we have a list which is 1 to 10, like the numbers 1, 2, 3 to 10, and they are sorted, right? So what we are going to do here is player A uses linear search and player B uses binary search. Our target here is 3. Player A doesn't know the answer and player B doesn't know the answer, but we are looking for 3, right? So what will player A do? Player A will say, look at the first element, the second, and then the third, right? And we got what we are looking for, which means player A takes 3 times, right? 3 tries to get to the answer. Note here the player which has the fewest tries has the correct answer and is efficient in whatever the problem is, right? So now let's get into some binary search and see how many tries we are going to get in searching for 3. We look at 5. Is it what we are looking for? No. We look for 2. Is it what we are looking for? No. We go on to 3. That means again 3 times, right? Which is 3 tries. And can we differentiate these two? They all performed the same. So it is hard to see which one performs better in here since they took the same number of tries. Let's play another game and see how these two again perform. So in here, we have a list which is 1 up to 100, and the target is 5. Player A uses linear search. We are going to search for the first element, the second, the third, the fourth, and the fifth, which means player A took 5 tries, right? Let's go on to player B, which is using binary search, and see how that player performs, right? So we look at 50. Is it what we are looking for? No. We go on to 25, 13, 7, 4, 6, 5. And we get to what we are looking for. That means player B took 7 tries, right? So in terms of this tries, player A got 5 and player B got 7. So player A wins, right? Let's play another game and see how these two again perform. We have the list, which is 1 up to 100. And we're searching for the element 100, which is at the end of the list. So player A uses binary search. We all know that player A is going to take, player A uses linear search, sorry, and we all know that we is going to take 100 tries. And player B uses binary search. So we look at 50, 75, 88, 94, 97, 99, and 100. So again, player B takes 7 tries. So from the previous game and this game that we played, player B takes the same number of tries, but player A takes 100 times. So who is the clear winner here? That means player B's strategy leaves A in the dust. So let's pretend the number of tries, it is the number of seconds it takes in order to complete a job. That means player A is taking 100 seconds to complete this job, but player B is taking only 7 seconds. Whew, what a massive difference. So let's take this example in this game into a real life problem, and let's look at the perspective of a company like Facebook. At the time of this recording, Facebook has 2.9 billion active users. That means simply, let's say we meet someone in the streets, someone with the name Zach, and you want to search for him on the Facebook, right? So simplifying how Facebook works, it has to search through these 2.9 billion users to look for the person with the name Zach. Note, the speed at which you find this person really matters, right? Imagine you're searching for the person, and let's pretend that name we just took, which is Zach, and let's pretend he's there at the list, at the end of the list, like he's the last user and in the Facebook list of users, right? So Facebook then says, come back after a few hours. Probably we have your results. Like after you just search for the name Zach, it says, come back after a few hours. Would you really use Facebook? No. So efficient searching algorithms play a big part in real life problems. So when comparing these two, which is linear search and binary search, we need to look at two aspects, which is correctness and efficiency. So correctness is, let's define it as whenever we give an input to our algorithm, right, the algorithm needs to provide an expected output to say we have found what we are looking for or we did not find what we are looking for. And then in terms of efficiency, efficiency is measured in two aspects, which is time and space. So in terms of time, it is how long it takes to complete a job. The less time you have, the more efficient you are. And in terms of time, it is known as time complexity. And then in terms of space, it is space complexity. That means the memory taken up on the computer to complete that certain job. You can pretty much have a faster algorithm, but it can be useless if it takes more memory than what you have on the computer. So that brings us to a concept known as the big O. So here, what we are going to do is define this. It is the theoretical definition of the complexity of an algorithm as a function of the size. Oof, that's a lot. But anyways, this is the useful notation for understanding both time and space complexity when comparing algorithms that solve the same problem. It measures how the algorithms perform in the worst case scenario, right? So let's go on to what we were looking at. So the last example we had here, we had our worst case scenario being in the list which we had 1 up to 100. Our worst case scenario was searching for 100. Linear search took 100 times, right? That means it is the worst case scenario. But in that worst case scenario, binary search took 7 tries, right? That means for the time complexity for linear search, we are taking it as it takes number of tries depends on what is on the list. That means time complexity is pretty much defined by using the worst case scenario. So here when we had 100 elements and we're searching for the 100 yet elements, that means the number of time we are going to take is n, right? Let's take it as like that. But when we get onto binary search, there is a mathematical relationship between what we have like on the ground. So what we have is a mathematical relationship which is known as the logarithmic of n. So in linear search, as value gets larger, the running time also gets larger as well. But in here, as the values grow larger and larger and larger, the running time decreases significantly by the log of n, right? So to make things simple here, linear search in terms of time complexity, it performs in terms of that time complexity and the big O notation, we can simply say that it takes O of n, right? That is the worst case scenario. But for binary search, what can we say? It takes O of log n, right? I do not want to confuse any of you here by the O of the logarithmic of n. But we are going to look at it later on in the future, which is probably some videos coming up through in this course. Then you can actually fully understand what this means, right? So this comparison is didn't cover much about linear search and binary search, but we just did cover what we did in the last video, and then in this video just explaining like theoretically what this means. So that has been it, guys, for this video. If you find this helpful, let me know down in the comment section. Hit the like button, subscribe to the channel, and I will see you in another YouTube video.